All right, so today we're going to carry on with our discussion about integration, which, as you know, is the inverse of differentiation. And so we're going to look at some very important theoretical results, and then we're going to introduce a new type of integral. So it should be very interesting. So let's go back to where we left off. We're in section 4.2. And after looking at all these different interesting results with the summation operator, we left off with our discussion of areas. Now, it turns out that in this section of the course, we're going to spend a lot of time analyzing the areas of rectangles. Okay, now there's other shapes that could be important too, but this is the one that we'll be using most often. So we're going to look at some basic background here before we dive into the theoretical results. So we'll start out by reminding ourselves that the area of a rectangle is nothing but the base times the height. Okay, that's one of those formulas that, you hardly ever forget. I mean, there's some of them you might forget, like the area of a parallelogram or something, but no, this one nobody ever forgets, the base times the height. For a triangle, we might run into this later on. The area is 1/2 base times height. We have all these other shapes that we don't need to deal with just yet. And now, by the way, they're also diving into the history of some of these results we'll be looking at here. You can read that if you find it interesting. But what we want to do right now is take a look at a curve. This is a function, and it's actually the function f of x equals negative x squared plus 5. So basically what you're looking at is a downward facing parabola. Let me just sketch it out for you. And let's say that we're interested in studying the area under this curve between the points 0 and 2. Okay, so this curve crosses the horizontal axis at radical 5, which is slightly greater than 2. So that means we're basically looking at this area here. Now, there's just one problem. This is not a rectangle. It's not a circle. It's none of our standard shapes. How do we figure out the area that is shaded here between the curve and the horizontal axis? That's the big question. And it turns out that the answer is with integration. But first, we have to understand how exactly integration is giving us this area. So what we're going to do is this. We're going to take this curve and we're going to break it up into a series of rectangles. We're going to use those rectangles areas to give us an approximation to the area under this curve. And we're going to do it in two equivalent ways. All right, so let me move this graph over here so you can see it better. So on the left, you can see, well, we have 5 rectangles. And if you were to add up their heights, you can see it would give us at least a rough approximation to the area under that curve. It won't be perfect, but it'll give us a decent estimate of what we're looking for. On the right-hand side, we're doing the same thing, except this time the rectangles are actually taller than the curve. And again, you can see if I added up the areas of those rectangles, it will give me an approximation to the area under the curve. It won't be perfect, but it'll give us at least a starting point. So what's happening here is that if you look carefully along the horizontal axis between 0 and 2, we've broken it up into 5 equal pieces. So we have 5 intervals, and from those intervals, we can define the heights of these rectangles. In the graph on the left, oh, by the way, within each of these rectangles, let's say we'll look at this one. This one runs from 0 to 2/5. And we are going to define, this is our left endpoint. And this is our right endpoint. Now, The same thing is true on the right-hand side, by the way. In this graph over here, what's different? Okay, well, let's look at these carefully now. If you see, um, in this diagram over here, the height of the rectangle is based on the right endpoint, meaning that the height here is actually equal to f of 2/5. Okay, this one is f of 4/5, et cetera, et cetera. And then if you want, you can plug in those numbers into that function, and you could actually calculate each individual rectangle's area. And then when you add them up, you would find that you have a number, which is based on the graph, is a little bit too small to be the actual area of the curve itself. Now, in the graph over here, you notice that the heights come from the left endpoints. This is f of 0. F of 2/5, 4/5, 6/5, and 8/5. And again, you can go in there, you can figure out the heights of these rectangles. You can then calculate their areas. And when you add up the areas, you'll see that it's a little too big compared to the actual area under this curve. So what do we do? The approach on the left means that our estimate is too low. The one on the right means that the estimate is too high. What can we do about it? Well, here's what we could do. By the way, notation-wise, what they want you to notice here is that each rectangle is represented by an index I. Okay, so we can think of this as I equals 1, 2, 3, 4, and 5. Same thing over here. Now, one more thing I want to just to label these properly. In this graph on the left, we're using the right endpoints to determine the heights of the rectangles. Over here, it's the left. All right. So now I think we're ready to see what comes next. So basically what's going to happen here is, oh, by the way, here they're going to give you a quick example of how you would actually calculate these areas. And so what's happening is that, as you know, the area of a rectangle is the base times the height. Luckily for us, the bases are all the same. They're all 2/5. That's the easy part. The height is the function itself evaluated, at least in this first case, at the right endpoint. Now, if you look at the connection between the I index and these actual numbers, you'll see that each of these endpoints could be represented as 2I over 5. Okay. So in other words, if you look carefully at it, for the first rectangle, 2I over 5 is 2/5. For the second rectangle, 2I over 5 is 4/5, all the way across. So in other words, the general formula for the right endpoints is 2I over 5. So what they're going to tell us is that the total area is the sum of f of 2I over 5 times 2/5. Okay, now they've done all the calculations for us. And now here, you see what they did here? They simplified it a little, but ultimately it ends up being 162 over 25, which is 6.48. You can double check that if you feel like it. I think we'll take the word for it right now. 162, approximately 6.48. Now that's for the diagram on the left, by the way. The one that's using the right endpoints. What about the other one? The only difference is the way we calculate, or the formula we use to represent the right endpoints. I'm sorry, the left endpoints. So instead of 2i over 5, it's going to be 2i minus 2 over 5. Okay, so you can see it right there, 2i minus 2 over 5. Actually, I should have written the other one here. Okay, so like if you look at the first one, I equals 1, the left endpoint is 0, and that's what you get if you plug in I equals 1 here. And you go across and you'll see the same thing. So now, when we calculate the sum of all of those rectangles, the base hasn't changed. So we add them up. And they will tell us that that adds up to 8.08, 202 over 25. And of course, as you can plainly see, that one's too high. Well, now what do we do? If we pick the method of right endpoints, we have a number that's too small. If we pick the method of left endpoints, we have a number that's too large. Well, what can we do? Now, this is the part, it's very difficult to draw this part properly, but what I'd like you to visualize is, let's just use the case of the right endpoints over here. And I'm going to try very hard to draw this properly. So here we have 5, okay? 5 right endpoints. What if instead I tried this? All right, well, it's really tough to do this by hand. So basically what's happening here is that what we're going to try to do to improve our results is have a larger number of rectangles, each with a smaller base. Okay, so in other words, here on the right, the 5 rectangles, the base is, in each of these cases, 2/5. If instead I tried 10 rectangles, each with a base of 1/5, it turns out that the area of the rectangles, and again, if we had a good diagram, it would be easier to see this. With more rectangles, the area of the rectangles gets closer to the actual area under the curve. So for this right endpoint method, which we just saw, the total area grows because remember, it was too small to start with. For the left endpoint method, the total area shrinks, of course, because it was too large to start with. So for the left endpoint method, the total area of the rectangles shrinks. And here's the interesting part. In the limit, as the number of rectangles increases to infinity, and the base of the rectangles converges to 0. So the total area converges to the area under the curve. In other words, if we keep having more skinny rectangles and they keep getting skinnier, but there's more of them, in the limit, as we get an infinite number of these rectangles, with each with base getting very close to 0, the total area will exactly match the area under the curve. So in other words, we're going to use limits to obtain our results. Aha, so limits are going to prove to be very important in this section. All right, so with all that background, now we can carry on. And now here's another example. And you can see that this is some arbitrary function, but it is continuous. That's an important detail, by the way. None of this, what we're about to see here, it all requires a continuous function. No discontinuities are allowed. So here's our new example. So yeah, okay, that's good. So between these two endpoints, this is what we're looking for. And again, it doesn't have a standard shape. We don't have a formula. So we'll end up using our rectangle approach. Okay. Now here, the width of the rectangles will be defined as delta x. Okay. So depending on how many rectangles we choose, the size of each, or the base is here. So it's a very straightforward approach. In other words, whatever the width is of the entire interval, let's say, for example, let's say A is 1 and B is 11, and I decide to have 20 rectangles. Then the width of each rectangle would have to be 10 over 20, which is 1/2. All right. So that's the base. The height of that rectangle Oh, by the way, I forgot to mention, as we increase the number of rectangles here, not only are we getting closer and closer to the true answer, but these two approaches are also converging to each other. Okay. In other words, eventually, if we have enough rectangles, both approaches, left and right endpoints, will converge to the correct answer. So anyway, they're showing us that the height could be defined in two different ways, left and right endpoints. So they're going to call it, looks like f of lowercase m is the right endpoint approach. And the index I reminds us of which rectangle we're referring to here, of course. Yeah, my graph isn't that good, is it? No. Um, hmm, I guess that'll do. No, I didn't draw it that well. Let me fix that if I can. Um, See, the problem is the way I drew this curve, there's not that much difference between the left and the right. So, and then for the left-hand point, that will be designated f of capital M, or rectangle I. Now, of course, the reason why they're doing this is because they want it to be clear that no matter which approach we use, we'll end up with the right answer as we take limits. Okay. Now, yeah, okay. So then what they're going to do is define the sums, lower and upper sum of these rectangles. Let's see. So yeah, let me copy these so we can see them better. Now, keep in mind with an integral, you're actually using literally an infinite sum. So the notation will be a little bit different. So we're going to call the sum. By the way, I wasn't aware of this, but in English, apparently, if the rectangles are under the curve, we say that they are inscribed. And if they're taller, they're said to be circumscribed. I'd heard those words before. I wasn't aware of that. So in the book, you're going to use that terminology. It's inscribed is the one where the rectangles are lower than the curve, and circumscribed means the ones above. And the sums will be defined as because on the left, you can see these rectangles are less than the total area. They're calling this SN the lower sum. This is the upper sum. Okay. The one in the middle, of course, is the correct sum. And now, so they're going to show us as an example of f of x equals x squared from 0 to 2. And you can see from the graph, this is the lower sum. This is the upper sum. And there's those words again, inscribed and circumscribed. I don't think they're going to ask you about that in WebAssign, but still, it's if you read this in the slides or in the book, you should be aware of what they're referring to. It's I mean, I guess we looked it up in Google, we'd see that this is correct. Now, these are the formulas for finding the endpoints. Okay, so remember we defined earlier oh no, you know what? I just realized I had these two written in. These are backwards. They want lowercase m to be the left. Okay, all right, let's copy these. And this is the formula for finding them. Okay, based on the index I. And remember, the index itself refers to which rectangle this is, just like before. All right, now. Okay. Anyway, what they're going to do is actually drive a formula for solving for the lower sum. And, you know, they plug in the formula that they just gave us. And by the way, they're using, so remember we had these formulas earlier with the summation operators. From the last time that we met. Here we are. In case we need these, here they are. This is slide 9. So basically what they're saying is based on those formulas for the left and the right endpoints, we can solve for these sums, the lower and the upper sums, by first the formula m of I, or m sub I, is, as we just saw, 2i minus 1 over n. F of that is what we're looking for. 2n is the base or the width of the rectangle. And so they're able to show, wow, that's pretty straightforward. So with all of that algebra using, and by the way, if you notice here, they did need the formula for I squared and I from what we saw back here. So already they've come in handy. Yeah, from this chart. This is a very important chart, by the way. We'll try to, maybe later on I'll make a separate copy of it. But anyway, after they're done, after all the dust settles, the formula is right there. Okay, well, that's pretty interesting. So Sn equals, and this is regardless of the function, it's, yeah, did you notice that the function itself dropped out of the whole thing? It's just 8/3 minus 4 over n plus 4 over 3n squared. Okay. So for x squared, you notice we don't need to square any x's. The whole thing depends just on n. So because that's what's going to change as we take the limit, as n goes to infinity, this is what we're going to need to solve for the area. Now for, a different function, they'll have to go through all these same steps and figure out a formula at the end here. And it will be different for each case, but it does end up eliminating any need to refer to the actual function. It's a very simple formula. Look at that. Now, the reason why this is done is because remember, it's n that we're taking the limit of. So we need our function or formula to be written in terms of n. And then doing the same thing for the upper sum. By the way, it looks like there's a typo here. We ultimately end up with 8/3 plus 4 over n plus 4 over 3n squared. So they're the same except for this part. Okay, and that's how you can see that the S capital N must be larger than S lowercase n. All right, now what's going to come next is that they're going to say, well, listen, let's look at a couple of quick examples. For example, what if I use 10 rectangles? Let's see what numbers we get. All right, this will only take a minute. Let's do this. All right, so remember the original case was x squared between 0 and 2. All right, so we have 8/3 minus 4/10 plus 4 over 3/10 squared. All right, I guess we can create a common denominator of 300. Um, yeah, that's right. Then S capital N would be 8/3 plus 4/10 plus. So they're pretty far apart. Now, I think, let's do one more of these. I think they want you to see, I know they wanted us to do 3 of these, but let's just try 100. Because what I would think they want you to notice is that as n rises, Sn will increase, S capital N decreases. And eventually they'll equal each other, and that number that they're equal to is the correct value of this area. All right, so let's just quickly run through it one more time for 100. Let's see. By the way, in a minute, I'll tell you what the correct area is. And fairly soon, you'll know how to do it too. It's not a trick. The way of calculating this, does involve integration, but here we're still looking at the theoretical background. So soon, very soon, you'll know how to calculate this area without all of this discussion about rectangles. You'll know how to calculate directly from an integral. But for now, we're going to look at some more theory, and then I'll show you how they actually calculated this in the first place. So what do we have? 8 over 3 minus 4 over 100. All right, I'm just going to get out a calculator for this one. I've got 2.6268. As a well, all right, 684 divided by 300 is 2.28. Great. So it did go up. That's good. And then for the upper value, let's see how low that one got. By the way, let's run up here for a second. 924 over 300 is 3.08. Two 2.7068. All right, so this is exactly what we were hoping for. They got closer, the smaller one got larger, the larger one got smaller, and the difference between them is actually quite a bit smaller. Okay, here they're really close to each other. Before they're quite a bit off, and if we did it again for 1,000, of course the same thing would happen. We're not going to do that, but we get the point. Oh, and by the way, the actual area here is going to be 2.667. So, even with just 100 rectangles, we're getting pretty close there. All right. So then they're going to explain to let's see. Now, there's also another approach that we could potentially take where we're sort of averaging out the two methods that we just used, the midpoint method. And so this is what they're asking us to do. So the area of interest, according to this, is going to be right here. So let's see, like here's their example. We're looking at sine of x between 0 and pi. right? So here we're going to assume that we've broken it up into four parts, four rectangles, that is. So, wait, oh, right. No, it is four rectangles, but we're looking at the midpoints. That's why it's confusing here. Those C's are the midpoints of the four rectangles that we chose. So by letting n equals 4, the delta x is going to be the width of this interval. Remember before, it's b minus a over n. In this case, b is pi, a is 0. Okay, so from one rectangle to the next, we have pi over 4. And then the c's are the midpoints of those rectangles. So in other words, C1 is halfway between pi over 4 and 0. And then we have C2 is pi over 2 plus pi over 4 over 2, which is oh, wait a minute. No, that's right. Halfway in between the two is pi, whoops, let me make some more space here. All right, well, then that means that C3 is halfway between 3 pi over 4 . Oops, no, I did the wrong thing now. Right. And then halfway between pi and 3/4 of pi must be 7 pi over 8. All right. Those are my midpoints. Okay. Now, what they want us to do, oh, they already did it for us. Well, all right. Well, now we know how they got those. Here's what they, now as you can see, this is a bit messy, but what we have to do in each case is we're going to take f of x or f of c for all four of them times delta x, which is pi over 4. And you can see that they plugged in all the numbers that we got. We got our c's, so we have to sign, this is C1, C2, C3, C4. Anyway, so when you go through all the math, you do end up with approximately 2.052. So, I mean, which one you use, I guess it's a matter of taste. They're all approximations. And Oh, wow. Here's an interesting question. Now, of course, we do not want to do this directly because it's asking us to add up something 22 times. Anyway, so you can see that they kind of left us hanging here. What are we supposed to do with all this? Well, you'll see in the next section. I guess they decided to save it as a surprise. Um, we're building up to a very important concept called definite integrals. Okay, the integrals we were doing before, as we'll see in a minute, are called indefinite integrals. We're going to now introduce something called definite integrals, where the point of it is to solve for an area under a curve and come up with a single number. So anyway, let's just check this out real fast. And in order to do this, we'll need to go back and look at those formulas one more time. We need the t-square formula from the slides. Actually, they used it I, but it doesn't make any difference. If you remember, that was slide 9. There we go. This is the one we want. All right, so with that in mind, and that of course means that we can write it like this. Oh, you know what I just noticed? They goofed here. This should have been changed to a T. All right. So what we're going to do here is use the properties of summation signs, the summation operator. All right. All right. So in here I've used t plus 1, and 2t plus 1. And now over here, if remember, when you're summing a constant like that, let's go back here. It's just Cn. So in other words, this is just equal to 3 times 22. Well, all right then. So 22 times 23 times 45 divided by 6 is, oh, it's an even number. So I've got 7656. There we go, D. And then they want this, use the limit process to find the area of the region between, let's see. Now, if you notice, they didn't specifically tell us how many, how wide the intervals should be. Hmm. All right. Well, so yeah, hmm. Oh, um, yeah, but this is just going to give us the lower and the upper sums, and then they didn't tell us. Uh, I don't think they gave us enough information to do this the way they want us to do it. That is. Um, well, we'll skip over this for now. Um, so then what's coming up next is yeah, 4.3 Riemann sums. So basically what you're seeing here is just everything we just did, um, except maybe potentially at a higher, more advanced level. But you can see they're taking all these intervals and they are breaking them up into rectangles to create what are called Riemann sums. And then they're building up to the definition of definite integrals. Then they'll give us some examples, but they're just basically extending the definitions we just saw a little bit further, and then they're introducing the concept of the definite integral. And once we get to that point, then we can see how we can use the rules of integration to find our results without going through all of these steps. This is all very interesting and all, but it would take forever to get a result if we have to do this every single time. So we're going to learn how to apply the rules of integration to solve for these definite integrals. Okay, and the difference between regular integrals and definite integrals is that we can specify a range over which we're interested in the integral. With a normal integral, we're assuming that we're covering the entire domain. So, all right, you know what? It looks like maybe this is something that can wait till next time. So this is 4.3. I don't think I have 4.4 open. Just out of curiosity, what's 4.4? Wow, it's taking its sweet time, that's for sure. Uh, the fundamental theorem of calculus. We can tell this is important because of the name. But again, this ties in directly with what we're doing here. It actually gives us it tells us, it formally defines the meaning of definite integrals. So, um, and then it also ties it together with other theorems that we've seen before. So yeah, the next couple of sections are going to be pretty involved. Let's put it that way. So, all right, anyway, I think we can stop right here and we'll pick this up next time. All right.